All right, everyone. Welcome to Calculus 3. In Calculus 3, we start talking about calculus in 3 dimensions. So in order for us to do that, we're going to go ahead and start here in section 12.1 with the three-dimensional coordinate system. It might be something that you've seen before, depending on if you've taken a different class where they use a three-dimensional coordinate system, or this might be completely new. One way or the other, we're going to walk through it. This should be a relatively short lesson comparatively. Some of these lessons are going to be very long throughout the year, but this one shouldn't take us too long. Okay, so let's go ahead and look at our outcomes. Our outcomes that we're going to talk about here are we're going to discuss the geometric idea of points, distances, planes, and spheres in the three-dimensional coordinate plane. Okay, so the three-dimensional coordinate plane, in order for us to talk about that, first thing we have to do is we have to be able to sketch it. We have to be able to draw it. The plane is divided into octants. So unlike before where we had quadrants, this is octants, meaning 8, and you'll see why. So when we sketch it, and this is the way I do it, everybody does it slightly differently, and the tilt that you want your plane, and you'll see that I do that for a very specific reason when we go through different examples, is going to depend on what you're actually drawing. So the basic idea is, and this part's pretty much the same always, this right here is the z-axis. And then what we have is your basic xy plane, but the xy plane is now basically like it's laying flat. So when we do the xy plane, you kind of draw it like this, where that's x and that's y. There's x, there's y, and hopefully you can see how that makes kind of a three-dimensional form. The easiest way to think about it's the corner of a room. If you think about the xy plane being the floor, and then the way the room goes up in the corner, that's the z-axis. That's the easiest way to kind of picture this. Now there's more to it, because it doesn't just go in that direction, it also extends. The x-axis obviously extends this way as well, and the y-axis extends out that way. That would basically be your standard xy plane, where the part in between the solid x and y would be your first quadrant. And then, of course, the z-axis also extends below as well. So it makes octants. So you've got the first octant, which is basically the positive x, y, z. And then, to be honest with you, the next part I'm not real sure about. I think the second octant would be following the xy, the normal xy plane. So it would be basically over in this range, but positive. And then your third one would be over in here, but positive, and then fourth one over here and positive, and then I think the fifth one goes into the first octant and then down. I'm going to erase those, but I believe that that's the way it works. The basic one is the first octant where everything is positive. Okay, so how do we plot points? Well, as you can see here, and it says plot the point 3, 6, -2 in several different ways. And that's because, just like in 2 dimensions, there were 2 ways that you could get to a point. Say we wanted to graph the point 1, 2. Well, that would be x is 1, y is 2. So I could go 1 in the x direction, 2 in the y direction, or I could go 2 in the y direction first and then 1 in the x direction. And it forms kind of a rectangle, which is why they call it the rectangular coordinate plane. If we want to graph the point 3, 6, 2, as you might expect, because now we have an extra piece here where the 3 represents the x, the y is the 6, and then the z, z is the -2. So it just follows alphabetically x, y, z. You could go 3 in the x direction first, 1, 2, 3. And then I could go 6 in the y direction. So 1, 2, 3, 4, 5, 6. So the idea is I would go 3 in the x, 6 in the y, and then we have to go -2 in the z. So this is the hardest part, because basically you have to go 2 straight down, so you're estimating the distance straight down the 2. So that right there would be your point 3, 6, negative 2. And that's what we're looking at. And there's obviously completely different ways we could go about doing this. So what I did was we went to the point, first of all, 3, 0, 0. Let me rewrite that. That doesn't look good. We went to the point 3, 0, 0. And then we came out to this point right here. Whoops, supposed to be a different color. Came out to that point right there. And this point over here would be the point 3, 6, 0. And then we went down from there 2 units. Now what I'm going to tell you is when we go to graph these things, the easiest thing to do, or actually the best way to do this, is to make sure whatever value you're trying to do, you stay parallel to that axis. So, for example, let's say that instead I wanted to go in the y direction first. So I could have gone out 6 this direction. Well, that's easy because it's right on the y-axis. And that point right there would be the point 0, 6, 0. And then from there, I wanted to go, let's use purple. And then from there, I wanted to go in the, but then we want to do the x maybe. So now we're going this direction. But you can see, hopefully, is that I'm staying parallel here to the x-axis when I go out that direction. And then we would go down to our point 3, 6, negative 2. And then, of course, you could also start in the z direction. And I'm not going to start writing every single possible coordinate on here because that would take forever. But we could have gone down to in the z direction first. Then we could go out in the y direction, 6 units. And then we could go in the x direction, 3 units. Or we could go down z, out in the x, and then over the y. And again, what you should see is all these different ways. I could go in the x, then down the z, then then down the z, then out the y. All of these are going to create still something which is in the rectangular coordinate system. In this case, it just happens to form a rectangular prism as opposed to just a rectangle. But there are multiple ways. In this case, there are, I don't know, you could count them up, but there are multiple ways that you could do this. Okay, so there you have it. There's basically the way to graph a point. Stay parallel to the axis. Make sure that your z-axis is your vertical and your x and y are on the xy plane. So it's a little bit different perspective that you're going to have to get used to. Okay, so let's go ahead and look at the second example. Plot the point -3, 1, 4 in several different ways. Well, I'll do at least a couple. This time I definitely will not do all of them. Again, the first thing is plot your x, y, z. This will take some getting used to, but you will get used to this. So there's z, there's x, there's y. And it looks like we've got a negative value, so I'm going to have to extend these just a little bit. You'll probably be able to do a much better job on your own paper. All right, so we want to do the point -3, 1, 4. So -3 is backwards 3 on the x, and then it's up 1 unit in the y direction, and then up 4 units. So we're going to go out 3 units in the x. We're going to go positive 1 unit in the y, and then we have to go 4 units in the z. So 1, 2, 3, 4, and it's a good approximation. It's also good to have these lines, the little dotted lines, because it gives perspective on what you did. Because if you just put a dot in the middle of the paper, you're like, I don't know what quadrant that's in. It could be in 3 different quadrants for all I know. It's tougher to tell. All right, in a different color, let's do it a different way. Let's this time we'll go in the y direction first. So we'll go 1 in the y direction. Then maybe this time we'll go 4 in the z direction. So we'll go up 4. And then this time we're going to go 3 to the left in the x direction, and we still arrive at exactly the same point. Again, I'm not going to finish off the whole thing, but that's the general idea. So hopefully that is not too confusing. Again, the hardest part is just visualizing. Most of this class is going to be visualizing stuff in 3 dimensions. All right. So what is kind of the point of starting off with all that? Well, we need some of that information, some of that visualization to be able to talk about how to find distances in 3 dimensions. So developing the distance formula in 3D is basically the same as it is in 2 dimensions. To do this, the distance formula is all derived from Pythagorean theorem. Pythagorean theorem. I hope I spelled that right. I should. Pythagorean theorem. Okay. So here's the idea. 2 dimensions, first of all. If I wanted to find the distance between 2 points, so we're just going to put any 2 points in space. To find the distance, obviously the distance between 2 points is a straight line, or as straight as I can draw it. To find the distance, what we should know is that we can find the distance by figuring out what the distance in the x direction is and figuring out what the distance in the y direction is, because what that does is that forms, okay, go away. Go away. I'll get it to go away somehow. Whatever. Sorry about that box there. What we've done is we've formed a right triangle. So if I know what the change of the distance is, so let's just call these points, oops, here we go. Let's just call these points, get a good color here, x1, y1, excuse me, and this point up here is going to be x2, y2. If I want to find the difference between the 2 x values, I'm really going from x1 to x2, because this point right here would really be the difference between those 2 x's. So going from x1 to x2, actually what this point is right here is x2, y1. If I want to find this distance, whoops, definitely did not mean to do that. Okay, let's try that again. If I want to find that distance, which we'll call A, and this distance, which we'll call B, the distance of A, the length of that side of the triangle, is just the difference between the 2 x values. So it's x2 minus x1. And remember, all this stuff comes from Pythagorean theorem. So really what we're trying to find here over here is D, which is the distance of that, that green line. So it all comes from Pythagorean theorem. A squared plus B squared, in this case we're going to call it D squared for distance, equals D squared. A itself is the difference between the x's. So that's x2 minus x1 squared. The b part is the difference between the y's, which is really just y2 minus y1 squared, and that's what equals d squared. So now if all I want to do is solve for d, I'm just going to take the square root of the whole thing. So the distance formula, which we know, or at least should know, is x2 minus x1 squared plus y2 minus y1 squared. Okay, not too terribly difficult. That's where the distance formula in 2 dimensions comes from. Now we're going to extend that idea to 3 dimensions. So let's draw our 3-dimensional there we go. There's z, x, and y. All right. Similar idea. The origin is 0, 0, 0. That's right here at the center. That's our origin, 0, 0, 0. I want to find the distance from the origin to some random point in space. Well, that point we're just going to put up here. Again, it's really difficult to tell exactly where that point is right here, but we're going to make this work. If I want to find the distance from the origin to that point, basically it's a straight line. And you might be thinking, well, how do I know? Well, yeah, good question. So what we need to do is we need to find the distance to that point, which is projected down into the xy plane. So really what I want to do is I want to project that point down to wherever it hits, which we're just going to call right there in the xy plane. So that point right there would be some kind of an x and a y value, but z would be 0. As a matter of fact, we're going to call our point up here just xyz. This point down here at the bottom would be the point x, y, 0, because there would be no height to it. Z has nothing. Z has no height there. So really, I can find the distance from the origin out to the blue point because really all that is going to be done by doing the distance formula in 2 dimensions. It basically is going to form a right triangle, because what you can see is that if I drop this perpendicular to the x-axis, what I've done is I've got an x distance, a right angle right there, and then a y distance. So this would be like my x, this would be like my y right there. So if I just do, and I guess for the sake of what we're doing here, we'll call this piece right here, just because I don't want to call it d for distance in this case, so we'll call it m. If I wanted to find that distance right there, m, it would come from x squared plus y squared equals m squared. Well, if I were to solve that for m, you would get the square root of x squared plus y squared equals m. Okay, that would give you that distance right there, which is basically the hypotenuse, or the distance from the origin to our blue point. But now I'm really interested in the orange distance. Well, that's the one I'm actually going to call D, and I'm going to call it capital D just so it's not the same as the one we just used. Well, we need to call this blue piece over here something, because now I've got 2 pieces of a triangle. I've got D and I've got M. But this blue piece over here, well, the easiest thing is literally it's just a z distance. It is the distance from the blue dot to the red dot, which is vertical. So that's z. So really all this is going to come from d squared equals m squared plus z squared. And you might be thinking, well, how can you do that? Well, think about this. Flat on the xy plane, where m goes out to meet the blue dot, right here, and it's harder to draw because it's visual, right here is a right angle, because that is literally perpendicular to the xy plane. So we have a right triangle. M and y happen to be the legs, and d is the hypotenuse. So that fits our d squared equals m squared plus z squared. Well, quite simply, we have something for m, so we're going to replace it. Because d squared is going to equal m squared, but m was this, so if I square that square root, I get x squared plus y squared plus z squared. So therefore, d, taking the square root, actually make that look like an equal sign here, is the square root of x squared plus y squared plus z squared. And that's, of course, the distance from the origin to any particular point. Well, if we want to extend this from one point to another point, it's just the difference in the x's, the difference in the y's, and the difference in the z's. So, final result here is that in 3D, our 3D distance is very similar to what it was in 2D. It is the difference in the x's, so x2 minus x1 squared, plus the difference in the y's squared, plus the difference in the z's squared. And that's it. That is your 3-dimensional distance. All right, I think we're going to go ahead and stop this video here, and we're going to come back and we will do a second video, and that'll finish us up.